Hello students. So next we'll proceed with our next topic, interrupts programming in 8051. So in this class we will be discussing interrupts in 8051. So by the end of this class you will be able to compare interrupts versus polling method. You'll be able to explain the purpose of the ISR, that is interrupt service routine, what is its use. You'll be able to list the 6 different interrupts that can be handled by 8051. Then you'll be able to explain the purpose of the interrupt vector table. Okay, fine. Okay, let us imagine a situation like a regular classroom situation where a class is going on in the classroom and suddenly there is a knock at the door, or attender gets in with some circular. So what usually happens, the staff or the lecturer stops whatever they're doing and they will attend to the knock or the person who is at the door, right? So that situation you can imagine or compare that to as an interrupt in any digital system. All right, so what exactly is an interrupt? Interrupt is an external or internal event that interrupts or calls for an attention, that is the best way, to the microcontroller to inform that the device needs its service. Okay, so interrupt is nothing but a signal. It's a call or a signal given to the microcontroller to inform that a particular device, whichever is sending the signal, needs the service from the microcontroller or the CPU. So in any computer, there is two ways followed in order to respond to interrupt signals. One method uses software instruction that jump to subroutine on the states of flags or the port pins. The second method responds to hardware signal, that is nothing but the interrupt that forces the program to call a subroutine. So subroutine is nothing but, here you can imagine similar to the subroutines what we had till now in our programs. So in terms of interrupt, those subroutines are particularly called as interrupt subroutine, service subroutine. Okay, so uh, so imagine a situation, there are 5 devices connected to the microcontroller. Okay, so in polling method, what happens? The microcontroller continuously monitors the status of a given device. Okay. Then if there is any request from that particular, any one of the devices out of 5, then the microcontroller would be responding to that, give the service. All right. So here what happens, generally in a round robin fashion, each of the device will be checked for a condition or a flag condition. All right, so this would be like time, a situation of time down the microcontroller, because every devices, it is look for a condition or check the status of the flag in that particular device, which would be an indication that a service is required. Okay. Remember in our previous programs, we used to have instruction JNB, jump or not bit set, TF, that is overflow flag, comma, target or here. So there, whenever we use time mode, so we were waiting for the overflow flag to get set. Until then, we were in that particular loop in the same instruction, right? So till the overflow flag was set, the CPU was not performing anything but waiting for the overflow flag to get set. Only after it was set, the next instruction would have got executed. Remember? Yeah. So there, what is happening? The CPU is tied up. It is not doing anything, or it is engaged now, waiting for the overflow flag to get set. So that is a situation like polling. Yeah, I had used this term earlier also. So in this polling method, CPU is unnecessarily tied up without, also wasting time and machine cycles. So waiting for a particular device uh, to know whether it requires a service or not. Okay. So this can be overcome by interrupt method. So in interrupt method, what happens? Whichever devices wants any service or attention from the CPU, it sends a signal. So that signal itself is an interrupt signal. So once that interrupt signal is received, then the CPU would halt or stop whatever it is doing and execute or run a subroutine that is called interrupt service routine. Okay. So here the advantage is that, say if 2 or 3 devices parallelly or simultaneously ask for request, then even in interrupt method, okay, those devices can be provided service based on the priority assigned. Okay, so that we would be discussing in the next sessions, interrupt priority and all. Okay, so also that in hardware method, you're not tying up the CPU. CPU can be allowed to perform some other task. Okay, only only when there is interrupt signal coming from the device, only then the CPU would be asked to respond to it or provide attention to that. Okay, so the comparison of interrupt method and polling method is tabulated here. You can read it. So it is summary of what I've explained right now. All right, so as mentioned earlier, for every interrupt signal, there has to be an interrupt service routine, or also called interrupt handler. Okay, so when an interrupt is invoked, the microcontroller runs or executes the ISR, interrupt service routine. So for every interrupt, there is a fixed location in the memory that holds the address of its particular ISR. That means for a particular interrupt, there will be a particular interrupt service routine of that particular interrupt, and the address of this ISR of a particular interrupt would be saved in a particular memory location where no other interrupt service can be saved. Okay, maybe you'll understand more about this when I show you the next slide with the different addresses and all. So uh, it means that there are many interrupts, and there are corresponding interrupt service routine for each interrupt, and the starting address of those ISRs are in particular memory location. So if you are tabulating that, then that table which holds all the addresses of the ISR, okay, is called interrupt vector table, which is clear in the next slide. So this slide clearly explains what I have explained in the previous 2 slides. So steps in executing an interrupt. So whenever an interrupt is received, what happens? So the CPU first, it finishes the instruction it is executing and saves the address of the next instruction on the stack. That is, whenever interrupt is received or encountered, then the particular instruction will be executed completely. And so you know that the program counter will be already pointing to the next instruction which has to be executed. So that next instruction will be pushed onto the stack, that is, save it on the stack. It also saves the current status of all the interrupts internally. Okay, all the other interrupt status will be saved. It jumps to a fixed location in memory, that is the ISR location where the vector table is saved. The vector table is nothing but interrupt vector table which holds the addresses of the interrupt service routine. So the pointer will be now pointing to the vector table, go to that particular address of the ISR. So the microcontroller gets the address of the ISR, that is the first step, from the interrupt vector table and jumps to it. That is, based on the particular interrupt, go to the address pointed by the ISR of that particular interrupt. Okay. Then it starts to execute the interrupt service routine until it reaches the last instruction. And we know that every subroutine ends with RET. But here, because it is the subroutine of interrupt, the last instruction will be RETI, interrupt from return from interrupt. That is a mail. Okay, subroutine for interrupt. Then after executing RETI instruction, the microcontroller returns to the place where it was interrupted. So the meaning is the execution of RETI is nothing but what? Pop the 2 bytes of address location that was tagged before execution of the ISR. Okay, now load it back to PC. So the PC will go back to the location where the interrupt was encountered, right? So the program counter is loaded with the address, okay, and then it starts executing from that particular location. Okay, so there are only 5 interrupts that are available to the user in 8051. But many manufacturers include a reset also as one of the interrupts. Okay, so that makes 6 interrupts in 8051. All right. So what is reset? What happens whenever there is a activation of the reset pin? We know that the CPU, whatever it is performing, it will halt or stop what it is performing and starts again from the initial stage, right? So which means that when the reset pin is activated, 8051 jumps to the address location 0000, the beginning location, right? So from there everything starts. Okay, so that's why the reset is also called one of the interrupts. The other two interrupts are set aside for the timers, timer 0 and timer 1, overflow flag. So whenever there is a rollover taking place, that is indicated by these two interrupts assigned for timers. Then there are 2 hardware interrupts set aside as external interrupts. So remember, P3.2 and P3.3 are used for external hardware interrupts, INT0 and INT1, right? Then one more interrupt is from the serial communication that belongs both for receiving and transfer of the data. So that is indicated by this serial communication interrupt. All right. So total 6 interrupts in 8051. So the table shows the interrupt vector table. Observe that, like each type of interrupt, its interrupt service routine are saved from locations given by the address indicated here. All right. So reset, its subroutine, it is starting from 000 location. External hardware INT0, it's starting from 0003. Timer 00B, external hardware, that is interrupt 1 at 0013. So other than reset, all other interrupt service routines are assigned with 8 bytes. Okay, so that what does it indicate? Every subroutine, interrupt subroutine should be as small as possible, because servicing or providing service to an interrupt means what? Responding to that particular type of a signal or an interrupt, isn't it? So responding to that means executing a particular subroutine. So the subroutine should be as small as possible. All right. So that uh, giving attention to the subroutine and coming back to the normal process. So it should not take much time. Yeah, that is the meaning. So one more thing, if you observe here, the ISR for reset, it starts from 000 location. And if you recall, all our programs, what we write, it also starts from 000 location, isn't it? And if you observe the table, vector table here, the beginning location starting from 00002 to this 23, that is, or 25H memory location, it is exclusively saved for interrupt service routines, or the vector table. It is allocated for this interrupt service routines. So whenever we write a program, we are not supposed to use these locations. So generally a good way is, when you write a program, always use ljump location, so that as you say org000, then immediately the next instruction should be ljump, so that you are saving or moving to some other memory location, uh, leaving this ISR location allocated for the memory, because they are set when the processor is designed. So you cannot use the ISR location to save your own program, right? So that is what I've explained here, as I mentioned in the previous slide, that whenever we write a program, the first location, if we save from 00, then the next instruction should be ljump main. Ljump main will be any address in the memory where you are exactly saving your program, right? Okay, so this is a good practice to follow, because you cannot use the interrupt vector table or the ISR location. Okay, so we know that there are 6 different types of interrupts that can be handled by 8051. So all, that is, 2 timer interrupts, 2 hardware interrupts, 1 serial communication interrupt, and 1 reset. Yeah. So on reset, that is, when you power up a microcontroller, all interrupts are disabled. Okay, that means they are masked. So meaning that even if there is any request from any particular type of interrupt, say timer 0 or timer 1 or any interrupt, then the microcontroller will not be responding to it. Okay, so in order to get the response, the interrupts has to be enabled by software method. Okay, to do so, we will be using a register called interrupt enabled register. Okay, so observe the interrupt enabled register given there. It includes all the bits there, starting from LSB. If you go from LSB, EX0 is the pin for external interrupt 0. Next is ET0, timer 0 overflow interrupt. EX1 is external interrupt 1. ET1 is timer 1 overflow interrupt. Then ES is serial port interrupt. Then ET2, timer 2, for a particular microcontroller 8952, which is not used here. Then 1 bit is used for user defined. You can use it for any of your applications. Then EA is for all the interrupt. Okay. Now, making these on power up or on reset, all these bits will be 0, which means that all interrupts are disabled. Okay, so if you want any of the interrupts to be enabled and to be responded, then you have to make these particular bits high. Okay, so 1 bit, that is D7 bit EA, will be enabling all the interrupts. EA on reset, it is 0. If you make it 1, then you are enabling all the interrupts. Okay, also you can also individually also enable the particular interrupt, whether timer 0, timer 1, extra interrupt 0 or extra interrupt 1, or serial interrupt. Okay, so what I explained in the previous slide is shown with an example here. Show the instructions to enable the serial interrupt, timer 0 interrupt, and external hardware interrupt. Okay, that is first A. Part B is disable or mask timer 0 interrupt. Then C, show how to disable all the interrupt with a single instruction. All right. So if you move IE register, interrupt enable register, with this value, the binary value is 1001 0110, then observe there the MSB bit you are making it high, that is EA is enabling all the interrupts. Also you have to individually enable, say serial 1 it is enabled, timer 1 it is enabled, timer 0 overflow interrupt is enabled, and an extra interrupt 1 is also enabled. Okay, so which means that the interrupt enable register is a bit addressable register, so you can individually set or reset the particular bit of this register. Okay, so the another way of performing the same thing here, see, set bit IE dot 7 means you are enabling all the interrupts. Set bit IE dot 4 you are enabling particularly serial interrupt. Then IE set bit IE dot 1 or dot 2 you are enabling timer 0 or extra interrupt 1 respectively, right? So as in part B question, disable timer 0 interrupt. So you don't want the timer 0 interrupt to be responded to. Then you have to clear that particular bit. So clearing that IE.1 will be, you will be masking that particular interrupt. So even if there is timer 0 overflow, so that will not be indicated by this interrupt, and the microcontroller will not be getting the interrupt signal. Okay, that is the meaning there. So clearing all the interrupts, you can simply make D7 bit 0. I hope you have got it. So we will discuss more on the next programming timer interrupts and other registers in the next session.